Good morning, everybody. We're trying to find the remainder, we'll call it R, when dividing an astronomically large unpronounceable number by 6. Now, the remainder we'll be getting is guaranteed, despite the immensity of the number, the remainder has to be in the set 0, 1, 2, 3, 4, 5. Okay, and those are the possible remainders when you divide any integer by 6. There we go. Okay, and just even the very first one's pretty big. You would have 3 to the 7th minus 3 to the 5th plus 2 times 3 to the 4th. Large number, and of course it's going to get larger and larger and larger. You'll notice there are 310 summands. That's a little misleading, but you have to actually subtract these two from each other and add 1. Just look at the special case from 1 to 2. That's actually 2 summands, but 2 minus 1 is 1. So this is actually equal to 312 minus 3, and then you have to add 1 for the reasons I just mentioned. So there's actually 310 summands, all of which are super large numbers. Okay, so there's got to be some sort of easier way to do this. Doing it manually is impossible. Okay, now, so of course, common techniques when you're working with polynomials is to factor, and that's the work that I've done right down here. I've taken p of x and factored it, and I ended up with this result right here. Now, this piece right here, the x cubed plus 2, would only be congruent to 6, I think, when x is, what, 2, 3, 4. 4 squared is 64. So if x was 4, you would have 66 in there, and that would be divisible by 6. But that's the only time this part is divisible by 6. So we have to examine this other piece right here, which is equal to x to the 4th minus x squared. Okay, so this piece right here, of course, is related to the lemma that you see down here. It's equal to it, in fact. Okay. Now this one is kind of a nice, it's a very nice result because you can see it's going to make all of this be 0 modulo 6, which means all of that would have a remainder of 0 when divided by 6. Okay, so the way to check this, it's clear it's true for 0, 1, and 2. 2 is very easy. 2 to the 4th is 16 minus 4 is 12, which is certainly divisible by 6. But I'll notice that 3 cubed minus 3 squared, or 3 to the 4th, excuse me, 3 to the 4th minus 3 squared is equal to 72, which is certainly divisible by 6. Okay, 6 times 12 is 72, so that's congruent to 0. And you can, let's see, I'll do a few more for you. Let's do, I'll skip 4, you can do 5. 5 to the 4th is the last remainder we have to change. Check. 5 to the 4th minus 5 squared is equal to 600, which is manifestly divisible by 6. Okay, we'll put 600 as congruent to 6. Congruent to 0 mod 6, excuse me. Okay, now you can check for 4, and this lemma really should state for all integers x, okay, because every integer has a remain, like we said earlier in the video. Okay, so this is for all x, a member of the integers. All right, so you see this is a big deal because we know that this whole piece right here is going to be congruent to 0, and all you're going to be left with is 1. So our summation is going to just be equal to the sum of 1 plus 1 plus 1, let's do our life-saving ellipsis here. Plus 1. And y'all, what am I going to write above this? 310 times. Okay, 310 times. Okay, and so this is equal to 310, of course. Equal to 310. Now you can do a quick division of 6 there, but you'll see that that's congruent to 4 mod 6. And fairly easy to see because 310 is what, 6 times, what is it, 51? Yeah, 6 times 51, which is 306 plus 4. And of course, 6 itself is congruent to 0, mod 6. And that's trivial. No condescension intended. Okay, so 4 is our answer. 4 is the answer to the problem, folks. Thanks to some algebraic simplification in this truth that a fourth power minus a squared power is always 0 modulo 6. Okay, so the answer to the question is R is equal to 4. Good day.